We continue our work with the talk of Professor Andrey Pilipenko, the zero noise limit of stochastic differential equations with L-infinity drift. Please, Andrey. At least I cannot hear you.
Your microphone.
Okay. This talk is based on my joint work with Ulrich Fjordholm and Markus Musch from University of Oslo. And let us consider ordinary differential equation. It is well known that if a function a is Lipschitz continuous, then there is a unique solution to equation 1. However, if a is not Lipschitz, then there may be multiple solutions. For example, if a is of the form, so a does not satisfy Lipschitz condition at 0, and if we start from 0, then there be many solutions to this equation. Okay, x plus is maximal solution, x minus is minimal solution, but there are a lot of other solutions, and every solution can be characterized as follows. We stay at 0 for some time tau 0, and then go up like this function, shifted to the right, or going down as this function, or we can stay forever at 0. And now let us add a small noise to this equation. And it is well known that the corresponding stochastic differential equation has a unique solution, even a unique strong solution, due to Zwontkin-Veretinikov theorem. And I would like to pass to a limit as epsilon tends to 0. And I would like to study a limit of x epsilon. And if the limit exists, then I will say that this limit is a natural solution to our original equation. By the way, it is not hard to see that if the vector field, if the function a is continuous, then any limit point of x epsilon satisfy initial equation dxt is a of xt dt.
Let me ask you, this limit points in the sense of weak convergence.
Yes. This is convergence in sense of distributions.
Yes, and do you know that they are non-random, or they will be random? They can be random, yeah?
Yes. The limit may be random. Yes, that's true. And today I would like to discuss the following problem: how to find the limit of x epsilon, or if there is, or whether there is the limit if a function a is discontinuous and just belong to space is essentially bounded. If a is essentially bounded, then it is not hard to see that this family of x epsilon, well, and we will start from 0. I forget to say that we will start from 0. Then this family is weakly relatively compact in space C0 infinity. But integral from 0 to point a of x s ds, so function x to this, is not a continuous functional. So we don't. So it is not obvious, or maybe it is not true that limit points of this will satisfy this equation if function a is discontinuous. And now let me, before let me explain what will happen and what are the solutions to the equation derivative of x is a of xt. If a is continuous, and then we will continue with other a also. X of 0 is 0. It is well known that if a is continuous and positive, then there is a unique solution. And now we will write it. Okay, let's make a formal calculation. Dx over a of x is dt, then integrate. Dx over a of x is t. Okay, let me write here dy over a of y. And let me denote this function by a of x. We assume that function a is positive. So there is no problem with this integral. And the function a capital is strictly increasing. I will consider only positive x's and non-negative x's and non-negative t. So there exists inverse function. And it's not difficult to see that the solution to this equation is just inverse function of a. I would like to say that if a is just continuous, but maybe non-positive, then there is a necessary and sufficient condition of existence and uniqueness to the solution of this equation, at least locally, local existence and uniqueness. And the condition is as follows. And condition is as follows. Assume that, so this is a result of binding. And if for any x0 such that a of x0 is 0, 0 of function a, there exists delta greater than 0 such that integral of x0 minus delta to x0 dz over a of z minimum 0 should be negative infinity, and integral between x0 and x0 plus delta dz a of z maximum 0 is plus infinity. Well, if we start from 0, if we start from the point x0 such that a of x0 is 0, and these conditions are satisfied, then there exists unique solution, and this solution is just x of t is x0. Well,
does it satisfy? Oh, yeah, it satisfies the initial data here, or not?
Yeah, and if a is, for example, continuous and positive, then there are no x0. Okay, if a is positive, then there is a unique solution. Always, we don't have to check these two conditions.
I don't understand why x of t equal to this x0. So the constant function is a solution. If x0 is not 0, it doesn't.
No. If a of x0 is 0 and these two are satisfied, then only constant function is solution.
So initial data. So our assumption that x of 0 is not satisfied. Yeah. So we do not consider the Cauchy problem. Yeah.
No.
Okay.
Okay, there may be such situations that. Okay, you're right. You're right. Then, for any starting point, there exists a unique solution. Theoretically, the picture may be as follows.
Which one? Then I don't understand.
You move like this. Here you have 0. And you may stay here forever, but may go further. So there may be the following picture of a solution, of non-unique solution, if you have a 0. Okay. Sometimes these conditions are called Osgood condition. Or these integrals like Osgood integral. Well, if a is not continuously differential, if a is not a continuous function, then we also can consider, well, not differential equation, but integral equation, because if a is just bounded measurable, then derivative of integral may not exist. So we consider this equation, and if a is positive, and if the integral, say this integral is finite, we can define the function a of x. Well, we assume that a is positive everywhere. Integral between 0 and x dy a of y. And this function is strictly increasing, so there is an inverse function, and it is not difficult to check that the following function, I will write it like x plus s, is a solution to this equation. Is a solution. to this equation. Or we can assume that a of x is greater than 0 almost everywhere, define this solution, and so on and so forth. The most interesting case will be the following. If a of x is positive for almost all x positive, and a of x is negative for almost all negative x, then if this integral is convergent and integral between between negative delta and 0 is convergent, then we can define also maximal negative solution. I will define it by x minus of t. And my aim is to find some conditions that ensure that the limit process for our small noise perturbation is the following process. With certain probability, it behaves like x plus of t, and with certain probability, it behaves like x minus of t.
What is x minus of t? I did not got.
Okay, if you have this,
Yes.
you can do the same calculation for negative x's. And if integral between minus delta and 0 is convergent, so a is greater than minus infinity, then similarly to this formula, you can define negative solution to this equation.
Thank you.
And now I would like to say a few words about history of this problem. So this problem was originated by Veritenikov and Bafika and Baldi. Veritenikov considered only symmetric, the drift only not symmetric, but he assumes that A is, how to say, odd function, minus A of minus X. And Bafika and Baldi considered quite a general case and characterized the limit process. And they found sufficient conditions that ensure that the process x epsilon converge to a limit where the distribution of the process x is concentrated on maximal positive solution with certain probability and minimal negative solution, and p plus p minus is 1. They only considered the case where coefficients are continuous or maybe approximated from above and from below pointwise by continuous functions. Bogdan, Oknin, and Wynn-Campois, they showed that any limit point of small noise perturbation satisfy Filipov solution for the ordinary differentiable equation if the drift is just bounded measurable. So let me say a few words about Filipov solution and what does it mean in our case. We have a function a from L infinity, and let us introduce the following function m small of x is supremum of essential infimum of A at the interval x minus delta x plus delta. So we have a function A which may be discontinuous. Take a point x, then take a neighborhood. Find essential infimum at this neighborhood, and then send delta to 0, and we define function m small of A. And similarly, we consider the following function m capital of x is infimum over delta greater than 0, essential supremum of A, where on the same interval. So we take the extension supremum and then send delta to 0. If A is continuous, then this function and this function equals A. And Bogdan and Kolsovs proved that any limit point x of t is a random process such that x of t has the following representation: f of x t, f of xs ds, where f of x of s belongs to the corresponding interval ma of xs to this. Let me show you an example that well, if A is continuous, then no problem. Then we have just solution to original or ordinary differential equation. But there are very bad examples of discontinuous functions, such that the set of so-called Filippov solution is too large. So let me show you.
Sorry, I did not get this. F is just arbitrary function which takes values in this segment or
no.
some. No.
They proved that if x is a limit point, so if there is subsequence such that x epsilon k converges in distribution to x, then for almost all omega, x is a solution to the following equation, where f is some function
unknown.
Yes, is a function, is some function. Well, it depends on, so x belongs to the set. Okay. Then this x belongs to the set of the functions such that this equation is satisfied. And I would like to say that this set may be very, very large if A is just bounded and measurable. For example, let us consider the following function A. Okay, it is known that it is known that there is a, so let me explain you what is bad function. Let A be a Borel set such that for any x and for any delta, Lebesgue measure of the set A in, okay, not x, for any A and B, any A and B, in AB is positive, and Lebesgue measure of A and for yes, and assume that this is also true. So this is complementary set. It is known that such sets exist. For example, imagine that you have a counter type set of positive measure, and then you take union of counter sets of positive measures such that this unit is dense in R, and complementary set also has a positive measure in every interval. And now let us consider the following function: a of x is 1 if x belongs to A, and 2 if x not in A. Then this function is just 1, and this function is just 2. So the set of solutions to the following Filippov equation is any function whose derivative is between 1 and 2. And there are too many functions that satisfy this property. Gradinaro, Herman, and Ronet, they considered large deviation problem for small noise perturbations of solutions to stochastic differential equations where A is non-Lipschitz continuous and have some Hölder continuity. Let me also mention paper by Delarue and Flandelin and Delarue and Maurelli, and their approach was as follows. They considered the drift A, which is, okay, in one-dimensional case, positive for positive axis, negative for negative axis, and has power asymptotics at 0. If we start not from 0, but from other point, then in this neighborhood we have positive function, positive drift, and the limit of small noise perturbation is just solution to ordinary differential equation. If we start here, then we go down. So everything happens in the neighborhood of 0. So they considered some properly selected neighborhoods, and these neighborhoods depend on epsilon, and studied the behavior of x epsilon of perturbed solution in this small neighborhood of 0. They studied probability to exit and times spent in the small neighborhood, and succeeded to find a solution to a small noise problem. And in multidimensional case, Delarue and Morelli did applied similar technique, and they studied multidimensional gradient dynamics where drift was Hölder type. And in series of works by Frank Brodsky and me, and then Alexei Kulik and Ilya Pavlukevich, we considered Hölder-Trap drifts in one-dimensional case, in multi-dimensional case, and we considered not only Brownian noise, but also self-similar noise, for example, Levy-alpha stable noise. And we succeeded to solve small noise problem. And our approach was the following. We considered some space-time transformation. So we looked at behavior of X epsilon at microscope, maybe something like Delarue and Flandoli did. So not exactly, but something like their approach. And we observed that after this transformation, the problem of behavior of X epsilon is very close to the following problem. Let us consider the following stochastic differential equation: a, let's say, b of xt dt plus dwt, where b is a Hölder type function. And the problem is how to find the probability that x of t converges to plus infinity or to minus infinity, and to study asymptotic behavior of xt as t tends to infinity. Well, and now let me consider the case when the function a is, so let me assume that the function a is positive almost everywhere, and the first result is as follows. Assume that for any delta greater than 0 and for any r greater than 0, integral between minus delta and r dy over a of y is less than infinity, then small noise perturbation of our ordinary differential equation converges in distribution to x, to the function, to deterministic function x plus. I recall that x plus of t is the inverse function of a, where a of x is integral between 0 and x dy over a of y. I assume here that a is just bounded and measurable function. And that's all. The idea of the proof is the following. At first, we know that the sequence x epsilon is weakly relatively compact. So to prove this, it is sufficient to verify that for every convergent, convergent subsequence converges to X plus. So further, I will assume that X epsilon K is convergent, but I will not write here K and just write X epsilon. Then I apply the Skorokhod representation theorem, and by Skorokhod representation theorem, it is known that there are copies of these processes defined on some new probability space, such that these copies converge uniformly to a copy of a limit as epsilon to X with tilde, where this is a copy of X. I don't know, is X, if X equals X plus or not, uniform, locally uniform. Now, what we can calculate for these processes? We can calculate probabilities that this process exit, for example, from any segment from above or from below. We can calculate some expectation, for example, expectation of exit time from any segment. And the only thing I know that the limit should be non-decreasing process because okay, X epsilon of t is integral of something non-decreasing plus epsilon W of t. This process converges to 0. So if X epsilon converge in distribution, then by Slutsky lemma, this sequence converges to the same limit. And this sequence is non-decreasing, so X is non-decreasing function, And let me formulate one simple statement that I will use later. Assume that Fn is a sequence of continuous function such that Fn converges to a function g as n tends to infinity uniformly on compacts, where g is strictly increasing and well, all of them were continuous, so g is also continuous. Let us introduce heating time, and let us assume that Fn of 0 is g of 0 is 0. Let us introduce the heating time. So if this is x, the moment when Fn hits x, I will denote by tau Fn of x. And assume also that for any x positive rational number, we have convergence of tau fnx to the heating time of the function g. Sn tends of some function f as n tends to infinity, where where f is a continuous function. Then f equals g. And so I will not prove this theorem. It's more less, or so it is quite clear that the limit is uniquely, if the limit is strictly increasing and continuous, then it uniquely defined by the heating times. And now let us discuss the processes x epsilon that converge to a limit. And I would like to prove that this process is x plus. In order to prove this, I can check that.
Andrey,
Yes.
can I ask you still about this lemma? Why do we know that these are heating time of the function g? We just know that we have some convergence. And
I have convergence to a function, and
yes,
I know that heating time converge to a heating time of some function. Then the statement is then f equals g.
What is the reason? Because it can happen that we have no convergence of the heating time to the limiting to the heating times of the limit functions sometimes.
Yes, the heating times is a discontinuous functional. Yes, you are true. But if the limit is strictly increasing and continuous, then they are. Yes.
Well, on this function, yeah.
Yes.
At this point.
Yes, at this
I
function.
see.
Yes.
This is the reason. Okay.
And now I would like to check that for any x, heating times of these processes converge in probability to the heating times of this deterministic function. And actually, the heating time of this deterministic function is just this function, integral between 0 and x dy over a of y. And if I prove this lemma, then I say, okay, I know convergence,
Uniform convergence.
Uniform convergence. I have convergence in probability. So by this theorem, for every x, there is subsequence that converges almost surely. And I enumerate all rational numbers, and I select the corresponding sequence that converges almost surely for this to the first x, then subsequence that such that heating times converge to second x, and so on and so on and so forth, and then I apply counter diagonal method, and I construct subsequence such that we have almost sure convergence for every rational x. This means that this subsequence converges uniformly to this function. But I know that all this sequence has, without subsequences, is already convergent. So if I prove this lemma, then I'm done. And well, how to prove convergence of heating times? Idea is straightforward. I would like to prove that expectation of a heating time convergence to this function, and that variance of the heating time x converges to 0 as epsilon tends to 0. And formulas for expectations, for example, are well known. For example, if we have a diffusion with some coefficients a and sigma such that the stochastic differential equation has a unique weak solution. For example, a is just bounded measurable, sigma is continuous and separated from 0. Let us introduce speed measure m dy and scale function for this diffusion, and introduce heating time for this diffusion. Then it is known that, for example, expectation of the following functional. So we wait before we exit from interval x1, x2 equals to the following integral, where g is so-called green function. So there are explicit formulas. And if f is, for example, if f is 1, then this expectation is just expectation of time of exit time from the following interval, and it can be checked that under our assumptions that for every delta and every r, this expectation converges to a of x, and in order to prove this, we proved the following lemma from approximation theorem, and the lemma is the following. Assume that we have two integrable functions, f and g, and we assume that function a, f is positive almost everywhere. G may be negative, for example, and this is approximating kernel. Then the sequence g epsilon converges to g in L1 and for almost all y from interval alpha and beta. And if we calculate this expectation of exit from minus delta r, then after some calculations, it can be shown that the expectation is equal to the following sum. P epsilon of x is the probability to exit from the interval minus delta r via upper bound if we start from x. So this is probability that tau epsilon x is less than tau minus delta. So the probability that we exit from above. If function a is bounded and satisfies Osgood condition, then it can be checked that this probability converges to 1 for every x between minus delta and r, as epsilon converges to 0. And now we have two expressions, and I would like to apply this lemma. So I multiply here by a of u and divide by a of u. And I remember that a is a positive function. And now I take f of z is 2az and g of u is 1 over a of u. This converges to 1, and by this lemma, the second term converges to integral of du over a of u. So excuse me, it will be not a of r, it will be, okay, let me start from 0, okay, from 0. Then this integral converges to 1 over a of u in L1. So the second term converges to a of x. And here we also apply the corresponding lemma, but you see, we have to integrate in this lemma, we integrate between y and r. So I have to multiply here by the indicator that u belongs to 0r. Also multiply by a of u, divide by a of u. And you see, the L1 limit of the inner integral will be as follows. Indicator of u in 0r divided by a of y. And we integrate here between minus delta and 0. So for those y's, this function is 0. So the first integral converges to 0. Well, we get convergence of expectations. We also have to it also can be checked that the probability that we hit r before minus delta converges to 1. We estimate variances and got the solution to our theorem that the limit of x epsilon is the function is this function. By the way, this function is deterministic. So if we have convergence in distribution to deterministic function, then we have convergence in probability in the space of continuous functions. function. So we have uniform, locally uniform convergence in probability to this solution. Another question is the following. And well, okay, what happens if the function a is not positive everywhere, but maybe integral of this function dy over a of y is minus delta is finite for any delta, but integral between r minus delta and r plus delta dy over a of y equals plus infinity. And let me write here even maximum with 0. So function a is positive, and we may have problems in R. For example, it may be the following picture, or a may be separated from 0, but a may be negative here or like here. So we have some problem in the neighborhood of R. Then the result is as follows. The sequence S epsilon converges to the function x epsilon of t. So let me write x epsilon weakly converge x epsilon, where this function is defined as follows: x plus of t equals the inverse function if t is less than r, and r if t is greater than or equal to r. So the limit function in this case is as follows. It grows up before it hits r and stay here forever. Or there may be another picture that we have asymptotic approaching to this level r. And the proof of this result is as follows. Okay, let us consider behavior of these processes before r minus delta. And we redefine our function a, say, like this. It will be a of x if x is less than r minus delta, and for example y1 if x is greater than r minus delta. Then solution to stochastic differential equations with these drifts and with drift r coincide until the heating time of r minus delta. So the limits also coincide up to a heating time of this level for any delta. Since delta was arbitrary, then it can be proved that the limits coincide up to the heating time of R, and the only problem is to check that the limit of x epsilon cannot go up after the heating. to prove that the limit cannot go up, you see, if you start from this point, then okay, if this happens, dy over a of y is plus infinity, then you never hit R, and this case is not interesting. And if we have the inequality, then this function hits R, and we have a problem above. We have a problem above, but the following integral for any delta is plus infinity, and we have somehow to check that any limit point of x epsilon cannot go up. And the idea of proof is as follows. Again, we use some comparison and some redefinition of the drift. And let us do the following. Let us consider the function an such that an of x is equal to a of x plus 1 over n. And let us consider sequence x and epsilon of t with this drift that perturbed by epsilon times Brownian motion. And we know that this sequence converges, converge even in probability, uniformly in probability to, let me write here like xn plus. And by comparison theorem, these processes for almost all omega are greater than these processes. So if this sequence converge to some limit, then this limit should be less or equal than this process for every n and for every omega. And it can be proved that xn plus converge to x plus as n tends to infinity, where x plus is the following process. It is stopped process. So we know that the limit of x epsilon is less than this process, and it coincides with this function before the hitting time. And the function a is positive between 0 and r. So any limit point cannot go down, but it cannot go up. So it must be like this. So that's all for today. Thank you for your attention.
Okay, thank you very much. And maybe somebody have questions or comments, please.
May I ask questions?
Sure.
So here you work in one-dimensional case, and therefore you can prescribe the limiting process precisely just solving the equation. And I just think how we can formulate the statement without solving of that equation. Can we formulate it via, say, the time spending and fixed point, that the time the solution spent at every fixed point is equal to 0? And then, for instance,
I'm sorry, in one-dimensional case or in multi-dimensional case?
No, say in one-dimensional case. So can we reformulate your statement as follows: that solutions to that the limiting process satisfies. I mean, it is a solution to the deterministic equation which spans 0 time at every fixed point.
Yeah, deterministic equation, probably yes. I think yeah. I think yes.
But what about the last theorem?
No.
You have the constant function after.
If A is positive, no. You're right, Andrey Anatolyevich, you're right. So the limiting processes are as follows. So if the drift is positive, then we go up as positive solution and then stop at the bad point. The bad point is the following, that integral of, say, r minus delta r plus delta dy a y maximum 0 is plus infinity. So
Okay,
this is the result.
But if the integral always converge, like in the formulation of your first statement,
then no problem at all. If it is convergent, then we have just expression. It is positive function, yes, strictly increasing, yes, and I think it is the only strictly increasing solution.
Okay, because as I understand, it would be the right formulation in multidimensional case when you can.
Unfortunately, in multidimensional case, there are not deep theory about existence and uniqueness of ordinary differential equations with discontinuous coefficients. And sometimes there are not. So this is just one-dimensional result.
Okay, and may also very short question, probably you should consider that as a comment. It is about the convergence of variance of stopping times. By the way, can we show that so more or less easily that every limiting process?
This was difficult.
No. I don't want to ask about convergence of variances. Just can we show more or less easily that the limiting process is always less or equal than this maximal solution x plus?
Maximum, it is less than.
It seems that it is not true, because if epsilon is positive, then
if epsilon is positive, we
I said that the limiting process, the limit is less or equal than x plus. Because if it is true, then you don't need to care about variance, because then you know that the stopping times are larger or equal than the stopping times of.
You see,
and then you have convergence of expectations. Therefore, you immediately get the convergence in probability.
Maybe you are right. Thank you. I will think about this. But you see, I don't know how to prove. If I know that the limit point satisfies equation x of t is equal integral of a of xs ds, then I can use your idea. But the function a is maybe terrible, maybe very discontinuous. And I don't know if x epsilon converges to x. Is it true that integral of 0 to t a of x epsilon ds convergence to this? So generally, this is not true. So in general case, this is not true. In our case, this is true. How to check, how to verify easily that this integral converges here, I don't know. So this is a really big problem, because x epsilon is a random process. It spends time at different points where A is discontinuous. Who knows? Maybe X epsilon spends more time or less time.
Probably you don't need equality. Maybe it is enough inequality.
Inequality?
Mhm.
Well, I don't know how to prove inequality too.
Okay. Okay. Thank you. I see the point.
Maybe other questions or comments, please. I also have some questions. What happened with the local times of these processes x epsilon? Because you can rewrite the last integral, which we discussed just a second before,
Yes.
via occupation formula, maybe then make some conclusions.
So it follows from the result that local times probably converge. But you see the local time of the deterministic function as a function of two arguments may be discontinuous.
Yes.
And it is a question, what does it mean? So maybe you have considered this local time like not like a function, but like a measure. And maybe this measure converge in some sense, because the integral of A of x epsilon SDEs, okay, you can write it like indeed like integral A of y local time at the point y dy. A is a function from L infinity. So to prove that this integral converge to some function, we have to not only to consider this as measures, maybe we have to demand more. So it is very strange convergence. So it will be not like weak convergence of measures. No.
Okay, interesting. Also, you mentioned such, say, Feynman-Cast technique for calculating of expectation and variance of the heating times. So, is it possible to control the speed of convergence?
No. These results, approximation results, are very delicate. And for variances, well, I cheated today a little bit. We can estimate variance if the function A is separated from 0. And let me explain you how we did this. So we have some x, we have heating time tau epsilon x. We represented this heating time as a sum of the following. Heating time of this level, then we start from this level and wait before we hit this level, and so on and so forth. And let us select this distance as, it seems to me, epsilon to the power, epsilon squared, I think this. And we say, okay, these heating times are independent, independent random variable. So variance equals sum of variances, and variance for this time is less than or equal to the second moment. And the second moment is less than the heating time for
Yes,
differential equation
I understand.
with constant coefficient. And for equation with constant coefficient, we can calculate it. And then we make conclusion that this heats faster, so second moment is less. And when we sum it up, we see that variance is less than some constant. It seems to me times epsilon squared. But my result was not for function a separated from 0. So we add to our function a 1 over n, make some comparison arguments. And by the way, we also apply idea of Vitali when we know the limit for this. Yeah, so it is not one-step proof.
I see. Okay.
I don't know how to control variance digitally for a without this assumption.
Okay, I see. Okay, thank you very much for interesting talk. Now we finish our work for today. Georgi, do you know who will be the next speaker?
Yes, the next speaker will be Konarovsky
Oh, okay.
about Dinh-Kawasaki equation.
So Vitaly already began to speak. And okay, see everybody next week. Bye.
Have a good day. Goodbye.